Yeah, Alex?
Yeah, what's the meaning of life?
What's the meaning of 42? Is that?
42?
That I don't know. I never read the book.
You never read the book?
No.
What book would I read if you were trying to get that up?
Well, to get 42.
No, not 42.
Oh, I don't know. I don't know. I'm one of those there's no meaning kind of people, sort of. But that's not a bad thing necessarily, right? Yes, Nathan? Are you allowed to what? No. You're not even allowed to have them officially due during study week. But the unofficial final deadline for homework, whatever it is going to be like Monday. See, no, Nathan, we can't do that because one of the TAs has to leave before the final to go to New York City to see the Star Wars premiere.
Different class.
Oh. Okay, what class?
I won't tell you anything. Guys, test us on that material.
I won't get him in trouble. He just needs to learn the rules. He doesn't know the rules. It's an honest mistake, I'm sure. Any other questions? Yeah.
Are you going to miss our class?
Oh, totally. Am I going to miss the class? Well, let's put it this way. Okay, Brendan first. That's a good idea. Maybe I'll make up the answers first and then make up the questions. Like 1, 3, 2, 4, 1, 2, 3, 4, none. Okay, well, in answer to your question, will I miss I will miss you guys a lot partly because, well, first of all, I've enjoyed your company this semester, and the bulk of you took 2200 last spring, so we've shared 2 semesters in a row together, and that's been fun. You put up with 2200. It was the first time I ever taught the class. It's always an adventure when you teach a class the first time, and you didn't hate it enough not to take this class, which is good. And anyway, so yeah, I will definitely miss you, and you'll have opportunities to take other courses from me if you like, because there's more advanced courses coming up. Like there's 2 of them next semester, and then there's going to be a brand new one the spring after next, supposedly. So anyway, you have the opportunity to break the record. The current record held by 2 students, Cale Smith and Omio Kudus, is 4 courses. What? You know them? They're both in Rockledge? Oh, okay. They took 4 courses from me. That was when I still had the NGRI going. So. Yes, Will. Sorry? Next spring? Oh, it's called Linear System Theory. It's EC 5210. It's about it's sort of like souped up multi-input, multi-output LTI systems with vector states, differential equations, difference equations, all that kind of stuff. Controllability, observability. If you're interested in control theory, that course is kind of central to it. So that's, and we're not going to have, unfortunately, we don't have the digital control course next spring because Professor Johnson is going to be at Cornell Tech NYC. So that course disappeared from the roster. And anyway. Any other questions? Okay, sorry about cutting off the prelim hand back. We can do that during the break and at the end of class today. And also apparently in the email I sent out to you, I misstated the exact problem that everyone's getting credit for. It's the last part of problem 9, the last part of the sampling problem. Everyone's going to get credit for that because there was a really subtle mistake there. And you can thank Stephen for giving you your 2 points back. And as a penalty for that, I think I won't give you yours or something like that. Anyway. Okay. Yeah. Oh, Erica?
Are you going to post a breakfast file?
No. You've seen enough, I think. You've seen, you know what it's going to... Just take those 2 prelims and put them back to back and think, okay, the final's going to be sort of like that. Yeah. And those, by the way, again, the prelims we posted online were not practice prelims. They were last year's actual prelims. they were not, yeah, Alex.
I think you might be able to do something like the 2200 where you like, answer questions sometime during the study period, like instead of time in the room.
Oh, that's an interesting idea. Yeah, the question is for those watching at home. Remember last year in 2200 we had evening prelims, and so we just didn't do lecture the day of the prelim. But we held class, and the class was just a question and answer session. And I'd be happy to do that, you know, at some point. I'm not going to be. I might be away the weekend of the 11th, 12th, 13th, but other than that, I'm going to be around the whole time until the final. So, you know, maybe sometime during study week. I don't know. I don't know how hard it is to get a room. What the market is. Could drum up some support. Submit a list of demands. No? Anything else? Yeah, Manish.
Is it going to be more focused on the after prelim 2 stuff, or is it going to be pretty even?
Question is, will the final be more focused on the after prelim 2 stuff, or is it going to be pretty much even over the semester? It's not intentionally focused on any one part of the semester. I try to be as sort of comprehensive as possible, but obviously it's impossible to ask you about everything. So, you know, yeah. And will you be responsible for anything that we didn't do in lecture? Well, there's that homework assignment, and there's something on there, signal flow graphs. It's very easy. And I'm expecting you, hoping that you'll read that part of the monograph and then, you know, do the homework problems and then look at the solutions and understand how to do at least an elementary one of those. What else? Anything else? The final, is the final going to be true, false? It's going to be a lot like the prelims. It's the same format. So you're going to have mostly that kind of question and then a couple where you have to do something, right? I mean, do some calculation. And you won't have a formula sheet. I'll give you any formulas that I think you need. And actually, there is precedent for the following, that during the final exam, someone comes up and says, could you give us formula blah? And I say, okay. And so I put it on the board because I didn't think you would need that. But someone wanted it. So I don't want you sitting around memorizing formulas, right? It's really about concepts. Memorizing definitions, that's another story. Anything else? Okay, so maybe Alex, could you send me an email reminding me to try to set up a little get-together with snacks or something, you know, tea and biscuits? It's a little too British. I don't know. Maybe, yeah, I like salty things better than sweet things. So chips, yeah, pretzels, you know, whatever. Okay. So anyway, as always, the last day of school, it's really hard to figure out what to triage, you know, what to try to cover. So I'm just going to see how it goes and whatever. So we're talking about the singular value decomposition, and that's for a matrix, a general matrix A in C to the m by n. So it's not necessarily a square matrix, and you have two forms for that. One of them is sort of written out in components. J equals 1 to R, sigma j, wj, vj Hermitian. And another one is written out as a product of matrices, W cap sigma v Hermitian. And I'm not going to write down again where the wj's and the vj's come from. The sigma j's are what are called the singular values of A. And they're all positive, not necessarily different. And here, A has rank R. And of course, the rank of a matrix is less than or equal to either the number of rows or the number of columns. So R is less than or equal to both M and N. And last time, we were talking about the special case where A is square and invertible. So special case, A is an n by n matrix, a square matrix, and it's invertible. Then R equals n. So you have n positive singular values for A. And all the matrices here, the W, the sigma, and the V, are square. They're n by n matrices, and all of them are invertible. In fact, the W and the V turn out to be what are called unitary matrices. So V, W, and sigma are all invertible. fact, V Hermitian V and W Hermitian W are the identity. So it's easy to find the inverses of those. You just take their Hermitian conjugates. And in this case, we have, it turns out, the singular value decomposition essentially for A inverse is this. Sum from j equals 1 to n of 1 over sigma j Vj Wj Hermitian, which is the same as V sigma inverse W Hermitian in matrix form. And since sigma is a diagonal matrix, taking its inverse is easy. Furthermore, you have this, that if you take the norm of any vector of the form AV, that's bounded from above by sigma 1 times the norm of V, and bounded from below by sigma n times the norm of V for all V in Cn. And we also have, in this case, a number kappa associated with the matrix A, the ratio between the largest and the smallest singular values. That's the condition number of A. And note that kappa lies between 1 and infinity. And what we were doing at the end of class last time is trying to characterize the sensitivity of numerical computations involving the matrix A to changes in the data that you plug into those numerical computations. And what we saw was that the condition number in some sense reflects that sensitivity. So we considered what I'll call problem 1, and that is to, given V and Cn, compute W equals AV. And we think of V as being some nominal value, V hat, plus some error, V tilde. So this is the nominal data. And this is the perturbation or error. And W, which is AV, is going to equal W hat plus W tilde, where W hat is AV hat. That's the nominal answer. And W tilde is AV tilde, and that's the error in the answer. So the question is, how much of an effect does an error in specifying the data have on the answer? How much does a V tilde push you away from the nominal answer W hat? And what we discovered was the following. We saw that the percent change in the answer divided by the percent change in the data, which we characterized as the norm of W tilde over the norm of W hat divided by the norm of V tilde over the norm of V hat, is less than or equal to kappa. With equality, that is to say, worst case, because clearly the more your answer changes in response to an error in the data, the worse the situation is, when the following two conditions hold. The data, the nominal data, V hat, is aligned with the V corresponding to the highest, to the lowest singular value, Vn, and the perturbation in the data is aligned with the V corresponding to the highest singular value, V1. So in some sense, the bigger kappa is, the worst case scenario is going to be for this kind of a numerical computation. It's going to be possible to have a really huge error in your answer result from a relatively small error in your specifying the data. Now, problem 2 is the inverse problem of this. Is there something wrong up there? I'm going to fix it before.
No, is it say aligned with the end?
Yeah, that top one is an N. It's not very visible. I should fix that so it's more visible. So here's a problem that's similar to this. Problem 2. Problem 1 was given V, compute AV. Problem 2 is given W, compute V satisfying AV equals W. So now, instead of plugging a V into A and finding W, what we're doing is solving for W in the equation AV equals W. Now, because A is invertible in this case, this is the same as given W in Cn, compute V equals A inverse W. What's the worst case scenario here? What do you think it's going to be? See if you can guess. What do you think the condition number of A inverse is? Denzel.
1 over the condition number of A.
Okay. He proposes the condition number of A inverse is 1 over the condition number of A. Any other proposals? Okay, how many people think that's right or probably right? Here, I'll inspire you to say yeah. Remember, the singular values of A inverse are 1 over the singular values of A. Okay, so how many people think he's right? How many people think no? How come?
Because the singular value is also flip order.
The singular values also flip order. So when that happens, what is going to come out to be the kappa for A inverse?
It will be pi 1 over pi n again. Because they flip order n also.
Yeah, it turns out, and your guess was just fine, but it was wrong. It turns out that the condition number for A inverse is the same as the condition number for A. So here's an observation. So it's also kappa, the same as for A. The reason is, we saw last time that thing up there, A inverse is the sum of those things. That's the SVD for A inverse essentially, but because the sigmas go down in size from sigma 1 to sigma n, the 1 over sigmas go up in size from j equals 1 to n in that equation. So the largest sigma of A inverse, and you said pi, that was the one error in what you said, sigma. The largest sigma of A inverse is 1 over sigma n. The smallest singular value sigma of A inverse is 1 over sigma 1, which implies that the condition number of A inverse is equal to 1 over sigma n divided by 1 over sigma 1, which is the same. Okay? So solving V equals A inverse W, given W for V, so thus in problem 2, the percent change in the answer divided by the percent change in the data So here, the answer is V, and the data is, or RW. And we model that as the magnitude of V tilde, or the norm of V tilde divided by the norm of V hat, divided by the norm of W tilde divided by the norm of W hat. That's going to be less than or equal to kappa. Again, because that's the condition number of A inverse. And when do we have equality? This is just to show that you can achieve this worst case scenario. Equality when the data for this problem is aligned with the W corresponding to the largest or the smallest singular value of A inverse, which is 1 over sigma 1. So it's when W hat is aligned with W1. So you can see that the W1 is playing the role that Vn played in the first one. And W tilde is aligned with Wn, because Wn is the W corresponding to the largest singular value of A inverse. So that's the story on condition number and how it influences the sensitivity of numerical computations to perturbations in the data. And this is the kind of thing people have to worry about when they're doing matrix computations with large matrices, all that. And you have to worry about when this comes into play, because whenever you do arithmetic in a computer, you're using finite precision specifications of the numbers, and sometimes your data are noisy and whatever. And my phone is ringing. Let me just see. Yeah, this toll-free number is calling me 3 times a day. What should I do? What?
Immortalize them on video.
Immortalize them on video note. Good idea. Okay, Nathan, next time. Yeah. Really?
If you want them to stop when they're trying to call you, have someone else pick it up and be like, no, this is not Professor Upchance, and then they'll stop calling you and they'll switch.
What if here's an idea. What if I go online and I say, where's this call coming from? And I find out it's some company that I have cable service with or whatever, or credit card. And what I do is I call forward that number to their customer service line. I don't know if I can do that though. I don't think I can call forward a single incoming number. Yeah, we could figure it out. Okay. All right. So anyway, that's condition number, all that stuff. Now, just to capture see if your intuition is good on this. I'm just gonna put up a couple of 2x2 matrices on the board, and you're gonna tell me whether these matrices are relatively well conditioned or relatively ill conditioned. Okay. So what about this matrix here, where epsilon is small? Is that well conditioned or ill conditioned? It's well conditioned. It's almost the identity. The identity is about as well conditioned as you can get. So this is well conditioned. How about this one? That's actually well conditioned, relatively speaking. What? No? Okay. What you're looking at is the largest singular value over the smallest singular value. Here, sigma 1 and sigma 2 both are on the order of 1, it turns out. Here, so this is well conditioned, sigma 1 and sigma 2 are both on the order of, I forget whether it's 10 to the 59th or the square root of 10 to the 59th. I think it's 10 to the 59th. So even though they're big, they're close together. Remember last time the intuition was if a matrix has a large value somewhere, a large entry somewhere, it has a large sigma 1. If it has a small entry in a key place, it has a small sigma n. How about this one? 1, 1. I'm just going to permute these elements here. How about that? What's that? Yeah, ill-conditioned. Ill-conditioned. It's ill-conditioned because sigma 1 is on the order of 1 and sigma 2 is on the order of epsilon. So this is a perfect illustration of sigma 1 is big when you have a large entry someplace. And in this case, that large entry doesn't hurt you too much because it affects all the singular values. Yep.
Do you know the singular values of these a priori, or are you, is there some trick here?
No, I don't know them. I know that like, no, there's no trick. It's just, I just happen to know them kind of from playing around with the equations and stuff. Okay, so that's an example. Now, the ultimate, ill condition would be something like this, 10 to the 59th, 10 to the minus 59th. That's ill. That's majorly, that's all caps ill. So. Yeah, you don't want to do numerical computations with a matrix like that. Okay, so anyway, that's square invertible. Now let's go back to the general case of a non-square matrix of rank R. So now let's go back to general A in C to the m by n with rank R. Then the SVD for A looks like this. A equals the sum from J equals 1 to R of sigma j, wj, vj Hermitian. Now, what if we take this equation and just kind of imitate what we did to get the inverse of an invertible square matrix in terms of the sigmas, the w's, and the v's? In other words, let's imitate, quote unquote, the A into A inverse thing to define the matrix that I'm going to call A sharp, also known to musicians as B flat, I suppose, as the sum from J equals 1 to R of 1 over sigma j times Vj, Wj Hermitian. That's perfectly legal. That matrix turns out to play an inverse-ish role for A. Does anyone know what the name of that matrix is, what that matrix is called? Pseudo-inverse? Who said that? Okay, and do you know who the pseudo-inverse is named after? In this country, at least? No? Pseudo-fake, yeah, exactly. Surrogate, ersatz, whatever. This matrix is known as the Moore-Penrose pseudo-inverse. So here's the terminology. A sharp is the Moore-Penrose pseudo-inverse of A. And it's named after, obviously after Moore and Penrose. You may wonder who they are or were. Penrose is actually still alive. He's a British cosmologist, mathematician, mathematical physicist, etc. He's a brilliant guy. He's never won the Nobel Prize or anything, but he's one of the smartest men in the world. And he got around 1989 or 90, he got really interested in sort of debunking the possibility of artificial intelligence, strong artificial intelligence. He wrote a series of books and got a lot of press for that. So you may have heard of him on those grounds. Moore, E.H. Moore, was an American mathematician who worked around the beginning of the 20th century. And actually if you know, like we have this thing in academia where you see who was your PhD advisor, who was his or her PhD advisor, and so on. You go back through the ancestry. And if you go back like 4 generations, Moore is above me. So one of his advisees was Garrett Birkhoff. One of Birkhoff's advisees was Marshall Stone. One of Marshall Stone's advisees was Chris Burns, and I was Chris Burns' advisee. So Moore is my great-grandfather or something in PhD lineage. But anyway, so the Moore-Penrose pseudo-inverse. Question, what is inverse-ish about it? So what's inverse-ish about A sharp? Well, to understand that, it's good to sort of step back and think about A and what it does as a linear mapping from Cn into Cm. Okay, so here's the side. So let's consider A as defining a linear mapping vector v goes to vector AV from Cn into Cm. So V is going to be an n-dimensional vector. AV is an m-dimensional vector because A is an m by n matrix. So this is a mapping from Cn into Cm. What does this mapping do? Well, I'm going to draw a little picture here. And this is something you probably saw in your Lin-Algebra course, depending on what book you used. So here we have Cn over here. And I'm going to draw it like this. And then we have Cm over here. I'm going to draw it like say this, whatever. And the mapping is V over here goes to AV over here. Okay, so what are these axes that I've drawn here? This is what I'm going to call, this is the null space of A. What happens to this whole subspace of Cn under the mapping? It gets collapsed to 0. So this whole thing gets collapsed to 0. And over here, I'm going to call this one the range of A. That's just the set of all things that this mapping hits, the set of all w's of the form AV. And this has dimension n minus r. This space here has dimension r. And this space, the range of A, also has dimension r when A has rank r. What does the mapping do? What it does is it collapses the null space to 0, and it maps this other subspace of Cn, which happens to be orthogonal to that one, and this one orthogonal over here, bijectively onto the range of A. Okay, so what is this subspace? This turns out to be the range of a Hermitian. But it's not so important that you know what that is, just that its dimension is r. So what does the mapping A do? Here's a description. Like if someone came up to you on Ho Plaza, right, and asked you to explain what's going on with this mapping V goes to AV, Nathan.
So you labeled that line null space of A, and then you say it had to begin with n minus r, and then you label it above having dimension r.
Oh, I meant, I'm labeling the same subspace. Let's fix that. Let's fix that. Thank you. I meant to say that this subspace has dimension r, and this subspace is the range of A Hermitian. That's what I meant to say, as you probably guessed. Okay? Now, for those of you who just walked in, like Harry, Justin, whoever else, you missed all the clues about the final. Oh my God. I had him turn off the camera. Don't tell them. Okay. I could be saying, don't tell them that that's not true. Or I could be saying, don't tell them the stuff I told you. And they're wondering, which I hope. Okay, so anyway, we can think of the mapping, V goes to AV, as like a two-step process. And this would be the answer that you would give on whole plaza if someone wanted a nice geometric view of what's going on. So we can view this mapping as happening in two steps. First off, take V and project it orthogonally onto that R-dimensional subspace, the range of A Hermitian. And then map the result of one over 2 the range of A in Cn. M. Okay? And if you want to think of how that's going on, or what's going on there, if you want to understand it more analytically, you can just look at the SVD for A. So the idea is, given V in Cn, step 1 leads to the sum from j equals 1 to r of V inner product with Vj times Vj. Okay? And then step 2, operate on this by A, i.e. step 2, yields what? It yields the sum from j equals 1 to r of V inner product with Vj times Avj. But remember what Avj is. Avj is sigma j Wj. And if you unwrap the inner product VVJ as Vj Hermitian times V, it comes out to be the sum from j equals 1 to r of sigma j Wj Vj Hermitian, all that times V, and that's just AV. Okay, so the mapping from the R-dimensional subspace in Cn to the range of A is really simple in terms of the W's and the V's. And that's the key to understanding what the Moore-Penrose pseudo-inverse does. So the mapping from the range of A Hermitian to the range of A is really simple in terms of the V's, because what happens is each of the V's, Vj maps to Avj, which is just sigma j Wj. And the inverse of this mapping takes Wj to 1 over sigma j Wj, which is Vj. Okay, so anyway, that's a bunch of stuff about how the linear mapping A acts. What about the Moore-Penrose pseudo-inverse? How does that act? It does the same thing in reverse, starting in CM. And let's just take the 3-minute break now, and I'll do that after the break. And for 3 minutes, I will give back prelims. YW? Just Sally? No. Oh, that's your net ID.
Yeah.
Oh, there we,
That's mine.
that's it.
Thank you.
This chalk makes it hard to grab.
Well, I emailed saying I wasn't going to be here, so I don't know if you.
I didn't do it yet. So.
Okay, cool. Thank you.
TSE.
TSE. There.
And I also pick up Brian's.
I'd rather not give anybody else's to anybody else. So Brian can email me, and I can put his prelims on my office wall or the bulletin board on something else. Hey.
Thank you.
All right. Yeah, that was thanks.
I always tell people I have 2 David Lees. One of them is L-E-E, and one of them is L-I. So I have to keep them straight. This one?
Yeah.
What's that?
Paramount?
Say it one more time.
Paramount? B-O-R. Is it my last
Oh,
name?
yeah, Cameron. Yeah, okay. It's in here somewhere. Yeah.
First name? Last name?
Both.
Joel Matthew? J.
Matthew. Yeah. Hey. I always say Kani when I read your name, but I don't know why. Sorry?
Stephanie Chen.
Stephanie. There. I know it's in here.
It's alphabetical, it's heck day.
I know, but maybe it got separated. No, I had it earlier. Here, oh, it's near the top for some, yeah. So Brian, have to put his. There you go.
Should have been somewhere around 80, right?
Yes.
CX34.
Sorry?
CX34. Check.
This one?
Thank you.
Mathematics told me that 1 10 to the 59th 0 1 has the singular values 10 to the 59th and 10 to the negative 59th.
That's not right.
Okay.
That should not be right. I don't understand that. Let me look at that. It should be they should both be high. They should both be high because the determinant and the trace. No, the determinant of A Hermitian A.
Oh.
Let me think. See, think of the determinant as the product and the trace as the sum. I'll look at that. Yeah. Okay, so anyway, this one, this matrix that I was talking to you about, apparently my calculations on that were wrong if Mathematica is right, or Wolfram, I don't know what, okay. Because I calculated that the singular values, which are the eigenvalues of A Hermitian A, were both on the order of 10 to the 59th, but apparently that's not true. So cross that one out just in case it's wrong, okay? Just in case. What's that? Huh. An easy way to do it, the product of the eigenvalues is the determinant of a matrix, and the sum of the eigenvalues is the trace of the matrix. And in this case, this is not the matrix we're looking at, though. We're looking at this Hermitian times itself. So, well, I don't want to spend time on it right now. I'll think about it later. Okay. So anyway, where are we? Okay, the Moore-Penrose pseudo-inverse. So think of A sharp. Remember, our whole goal here is to figure out what is inverse-ish about the Moore-Penrose pseudo-inverse. So defines a mapping W goes to A sharp W from Cm to Cn. And what it does, similarly to the mapping V goes to AB, so that mapping also goes in 2 steps. The first step is going to be, referring to this picture, take a W in Cm and project onto the range of A orthogonally. And then map that via this inverse mapping. The Wj goes to 1 over sigma j Wj, or Wj goes to Vj, to something in that other subspace, the rank R subspace, range of A Hermitian. Okay, so let's look at that in components, as we did for the mapping V goes to AB. So 1 results in sum from j equals 1 to r of W inner product with Wj times Wj. Because the Wj's from 1 to r form an orthonormal basis for the range of A. And then 2 results in this. The Wj goes to sigma j Vj, not Vj. Wait. Yeah, the Wj goes to Vj. Sigma j Vj, not Vj. And I think I might have to fix that one too. No, this is, yeah, this is. That has to be. Ugh, okay, I want to get this right. So A inverse Wj is going to be A inverse times 1 over sigma j AVJ. So this is 1 over sigma j. There we go. There. Okay, so this results, applying A to this, or A, that inverse mapping results in sum from j equals 1 to r of W inner product with Wj times 1 over sigma j Vj. And if you sort out this inner product as Wj Hermitian times W and reorder the terms, you get the sum from j equals 1 to r of 1 over sigma j Vj Wj Hermitian, all that times W, which is A sharp W. Okay, so all I was trying to do is show you that you can think of this mapping A sharp as a two-step process, as well as a mapping A. One of them goes from Cn into Cm, the other one goes from Cm into Cn. Now there's a really succinct way of summarizing this in equations, and I wanted to draw the pictures first because those are useful for some people, they're useful for me. But here's the most, I would say, compact summary of what is inverse about A sharp. So here's the summary of what's inverse-ish about A sharp. It's two statements. It's two statements. That if you take A sharp and operate on AV, you get V whenever V is in the range of A Hermitian. And whenever you take A and operate on A sharp W, you get W for all W in the range of A. So in a sense, what it does is when you restrict it to those r-dimensional subspaces that map 1 to 1 on each other, the A sharp inverts the mapping that A defines between those two subspaces. Okay. All right, so that's the Moore-Penrose pseudo-inverse. Now, there's formulas for the Moore-Penrose pseudo-inverse in special cases where the matrix A has full rank. And I want to give you those. So here's a special case. Actually, it's two special cases. First case is when A has fewer columns than rows. So M is bigger than or equal to N, and A has full rank N. Then it turns out that A sharp is equal to A Hermitian A inverse times A Hermitian. So this is what A looks like here. A looks like this. And A sharp looks like this. So this is M and that's N. The other special case is where M is less than or equal to N and A has full rank M. Remember, the biggest the rank can be is the minimum of the number of rows and the number of columns. And in this case, A sharp turns out to be equal to A Hermitian times A Hermitian inverse. So in this case, A looks like this, And A sharp looks like this. And if you just Wikipedia on Moore-Penrose pseudo-inverse, sometimes it pops, these formulas pop up. And you think, oh, that's the Moore-Penrose pseudo-inverse, very easy to write down. But these formulas hold only when A has full rank. When A doesn't necessarily have full rank, those formulas don't hold. And you can check that when A is square and invertible, that is to say when M is equal to N and A has full rank N, these reduce to the formula for A inverse. Yeah. Sorry? What is? Full rank is the biggest the rank can be. Whenever you have an M by N matrix, the biggest the rank can be is the smaller of the number of rows and the number of columns. That's one of those things about rank. And in fact, I should put the full in parentheses because that's just a sort of an aside that when it has rank, when it's M by N and it has rank N, that's the biggest the rank can be. Okay, now a couple of words about uniqueness here. This I don't want to dwell on, but you may have noticed, I've been referring to the singular value decomposition of a matrix, A. But there's actually some wiggle room in defining the singular value decomposition. Why? Well, remember how we found the V's and the W's? They were orthonormal bases for eigenspaces. What if you have one eigenvalue for the whole matrix A Hermitian A? Then the whole of Cn is going to be the eigenspace corresponding to that eigenvalue. You can pick any old orthonormal basis for Cn as the V's. So there's non-uniqueness going on there. And I don't want to dwell on that. The cool thing, though, is that even subject to that non-uniqueness, the Moore-Penrose pseudo-inverse always comes out the same. In other words, like if you define the Moore-Penrose pseudo-inverse this way, no matter how you chose the V's and W's with respect to the wiggle room, you get the same matrix A sharp. And the monograph actually is a proof of that, if you doubt me. So even when the Moore-Penrose pseudo-inverse doesn't come from these simple formulas, these sort of Wikipedia-level formulas, it's uniquely determined. Okay, so finally, I just want to talk about three sorts of problems that one encounters and how singular value decomposition spits out solutions to these problems right away. So if someone comes up to you, and this would be something that would more likely happen, say, in the Johnson School or the Hotel School or something like that, it says, I have this linear least squares optimization problem I want you to solve. Sometimes you can give them the answer in one line. Okay, so here are three problems in the realm of linear least squares optimization. And their solutions, they're SVD inspired, so to speak, solutions. Okay, so we've already used up problem 1 and problem 2 in this lecture, so let's do problem A, problem B, problem C. Problem A. Now we can't use A because we're going to use A for the matrix the whole time. So Roman numeral 1. Problem Roman numeral 1. You're given an M by N matrix A. So A is in C to the M by N. What you want to do is you want to find, which one do I want to do first? How about let's minimize the norm of AV subject to the constraint norm of V is bigger than or equal to 1. Okay, so this is a constrained optimization problem. You want to find a V that minimizes AV norm, and the V is going to have norm at least 1. So this is a non-trivial problem to solve. in general. Okay, now there is a trivial situation here that we want to avoid. And what's that? Suppose A looks like this. In other words, it has fewer columns, or fewer rows than columns. What's a trivial way to minimize the norm of AB? Well, 0 is trivial, but that doesn't satisfy the constraint, v bigger than or equal to 1 in norm. Alex? Well, why does A have a null space? Any matrix that looks like this has a null space. The rank of this matrix is at most equal to the number of rows. The number of columns is bigger than the number of rows. The null space has dimension n minus the number, n minus the rank. So this matrix is always going to have a non-zero vector in its null space. And so we want to avoid that situation. So assume, to avoid triviality, that rank of A equals n. So that null space of A is the set consisting of just the 0 vector. Okay, so what is a circumstance where this problem might arise? Think of it this way, like say you're a manager, right? And you have a bunch of staff members, and you want to dole out a certain amount of work between your staff members and get the work done as quickly as possible, right? The constraint v bigger than or equal to 1 in norm is going to correspond to, I want to get at least this much work done. And the way you dole it out is the way you apportion the work between the entries in V. I'm talking very roughly here. And think of the norm of AV as how long it takes your staff members to get the work done. So what you're trying to do is minimize the time it takes for the staff members to get the work done, subject to getting the work done. In other words, picking a V, allocating the entries in V so as to minimize that objective function. Okay, anybody care to guess what the solution to this problem is in terms of singular values without looking at the monograph? Dan? I don't know. You tell me. Okay, sorry. Okay, solution. V equals Vn, the V vector corresponding to the lowest singular value. The reason is that we've seen that the norm of AV is at least bigger than or equal to sigma n times the norm of V for all V, with equality when V is aligned with Vn. And you clearly want to let V equal to Vn because Vn has norm 1. If you align it and it's bigger norm than V, and then you're going to have a larger value for AV. So you pick V equals Vn itself to minimize AV over all C0s times Vn, subject to C0 bigger than or equal to 1, which is the same as V bigger than or equal to 1 here. Okay, so that's one problem. Another problem where singular values spit out the solution. Roman numeral 2. Oh, not effective chalk on the list. Given A again, what you want to do is maximize the norm of AV subject to the constraint norm of V less than or equal to 1. So this is exactly the opposite problem in some sense. You're maximizing the norm of AV subject to norm of V less than or equal to 1. And where might this problem arise? Suppose your vector represents like an allocation of your money among different investments, say. Your high-risk Janus capital fund versus your, municipal bonds or whatever, whatever. So how you allocate your money is how you distribute the entries in V. The constraint V less than or equal to 1 means you only have so much money to allocate. The norm of AV, maybe, represents the expected return on those investments. So you want to maximize your return by distributing your money among the entries in V, subject to the constraint that you have only a limited amount of money. What do you think the answer is, inspired by problem Roman numeral 1? V1. Were you going to say V1? Okay, so unanimous choice is V1. And the reason is that AV is at most equal to sigma 1 V1 for all V's in Cn. And it's achieved, that equality is achieved, that's sigma 1 V, not sigma 1 V1. Equality when V1 is aligned with V, or V aligned with V1. And choosing V equals V1 satisfies the constraint. Okay, so these are two constrained linear least squares optimization problems the singular value decomposition helps you solve. Okay, now for an unconstrained problem. And by the way, there's probably courses in OR where, like, the first week of school, you dispose of all this easy stuff right away, and then you get into hard. Has anyone taken an OR course that deals with these kind of things? Alex, is that am I right about that? Not really. Not really? What course did you take?
Took optimization 1, and I'm also taking game theory.
Is optimization 1 a 4,000 course?
3,000.
3,000? But they must have done linear least squares at some point.
It was all linear programming.
Oh, okay. So all linear programming.
I think Optitude does that stuff.
Yeah, this is not linear programming. Why? Because the things we're trying to maximize are two norms, right? They are sums of squares to the 1/2. Linear programming, you're trying to maximize or minimize a linear combo of entries in a vector. Okay, so that's, yeah. And so do you do all that new stuff, relaxation, and yeah. See, that didn't even exist when I took linear programming in school. So yeah, that's pretty cool that you're learning that. All right, finally, problem 3. Given A in C to the m by n, and W in Cm, okay, so W is over in the range space of the mapping A to V. Find the V in Cn of smallest norm that minimizes the norm of AV minus W. Okay, so let's consider what this problem is all about. A here is an m by n matrix. Its range might not be all of Cm. So you might not be able to hit every W in Cm, right? But you want to get close to a certain W. Someone comes up to your whole plaza and says, you know, I want you to pick me a V, allocate your resources into a V vector so that AV is as close as possible to W. And I want you to do that with the smallest possible energy, so to speak, the smallest possible norm of V. So we've got like a two-part minimization problem here. We want to minimize the distance between AV and W with a smallest norm V that does that. Okay? What do you think the solution to that is? Okay, let's go back to our pictures. We have 1 minute and 41 seconds left. So here's Cm over here. Here's the range of A. And here's W. So we want to get as close as possible to W in the range of A. So we project onto there, right? Call this W hat. So we're going to find a V that maps to W hat, and that V has to be of smallest norm. And over here, in Cn, you've got the, let's make this be the null space of A. And any V that maps over to that W hat is going to solve our problem. And if I choose a V that's over here, that's the same as mapping with this V. So this is going to be our answer V hat. It's going to be the V hat perpendicular to the null space of A that maps to W hat. And what is that in terms of things we've talked about so far? I know, it's hard to keep up. The last day of school, we're all tired. We're all like, but I'm hoping somebody maybe. Okay, I'll give it away. I'll give you the answer. The solution is A sharp W. The Moore-Penrose pseudo-inverse operating on the vector W. Why? The Moore-Penrose pseudo-inverse, what it does is it takes any W over here in Cm, projects it onto the range of A, and then maps it back to a vector over here in this space that's perpendicular to the null space of A. That is going to be the smallest norm V that maps to that W. Got it? Denzel, good. Okay, somebody got it. All right. Rishi?
I got it.
You got it? And by the way, he's the one who has to leave early to go to see the Star Wars premiere in New York City. Yeah. What's that? Boston? What's that? Oh, you only want to, right? Yeah. Okay. All right. So I'll see you guys in a couple weeks and maybe next week. We might have a little get-together.